right, good morning. I had quite a busy day. I went to give a continuing education lecture on water and wastewater to some operators in Covington yesterday. So I know I received at least one email about the homework. I'll get back to you. Apologize, I haven't done so yet. If you haven't turned in your homework, I'm actually okay if you turn it in by the end of the day today. I think Moodle will accept it. It'll mark it as late technically, but I'm not going over the homework today. So if you need to wait till I respond to something or whatever. But at the end of the day, for the homeworks, like I told you, I'm checking them for completion that your effort was there, and so it should be a learning tool. And I'm gonna respond if I have not yet. Help you through that learning process. So that's something just to be aware of. I think we're on track to cover everything we need to in time for the exam, given that I'm going to have a separate exam review session. So as part of the participation today, there's a front and a back here, so we'll get a couple answers to this. I'm going to guide you through this a little further than we went last time to help you kind of navigate the problem itself. And then another thing on here is kind of what's been clear, what's been unclear. You're welcome to write me something to say like, hey, I'm really uncomfortable with the in-class exam review or something like that, right? You're welcome to give me that sort of feedback, even if I didn't ask specifically for that. You're also welcome to only put your name on the side that has like your quiz answers. What I'll do is I'll count the answers themselves as accordingly, and then I'll flip it over and just kind of ignore who wrote what. So if you want to be that, it's not truly anonymous, but I'm going to treat it that way. So if you wanted to write something that you might think I'm uncomfortable with, feel free. I should have some extras too if you really wanted more anonymity, you're welcome to do that. Okay, so we left off on Tuesday talking about this particular problem. Wrote up a few of the equations we were going to need. On our little participation sheet today, what I'm going to ask for is the value for G that you solved for, the value for the omega, that flocked volume that you solved for, a value for the n naught over n that you will need to solve for, and then a final answer. So I'm gonna write those up, change the slide real quick, and again, like I said, kind of structure the problem a little more. I know that at face value, it's certainly easy to kind of get stuck in terms of where do I actually go with the problem. All right, so the problem itself says we're going to improve the settling of this particle we looked at a couple lectures ago for sedimentation. So we've destabilized the particles, and it said we've done that completely. And so that tells us a little bit of information about our alpha value here, right? This guy. So complete destabilization means that should go to 1, right? So that's a point there. Added alum, and it passed through 2 side-by-side well-mixed flocculation chambers. So really, before much of anything else, we ought to draw this up and say we've got flow going through 2 side-by-side chambers where we can look at, this was 3 mgd, and so it would be natural to draw up what that looks like in practice. And we're given some volume here that you can solve for. They're mixing. And then we're getting the effluent there. And chances are these streams will probably be mixed back together into the same line. Okay, so we're given some parameters there. We're given these particular conditions, some power, all that, given a few parameters from the previous problem I wrote up here. And ultimately the question is, what is the average diameter for the aggregates leaving? So the deal is we're causing the particles to stick together. And when we do that, they're going to go from these smaller particles into larger particles. We're going to assume that the volume of these particles is conserved. So there's no, like if we started with one volume unit for one particle, and we've got 10 particles in each of the final aggregates, then we have 10 volume units in the next one. And if we assume that that just becomes a perfect sphere, then we can do a diameter check, right? We can compare the diameters across the two conditions. Okay, so let me tell you what I'll ask for on this little sheet of paper. I'll pass those out in a minute. But really, we're going to need to find a couple of things here. What is the value of G? What is this value for omega? I'm also going to ask you for a value of n naught over n, and then a final answer would be the diameter, we'll say, of the aggregate. Leaving the chambers. Okay, so as a reminder, we said for the value of G, we have a formula that's the power divided by the dynamic viscosity times the volume of the basin. The omega here, we have an equation, and this is going to be the number concentration of the initial particles times essentially the volume of those initial particles, which would be their diameter cubed times pi over 6. For the n naught over n, we're going to need to find k. And I didn't ask you to give me this specifically, but it could have been another thing that we'll need. But along the way, we're going to need it because we have to solve a mass balance involving some reaction. The reason we need G and omega is because we need the K. We have an equation for K, and we said that was going to be 4 times, or I think we wrote it, this alpha, is it, times 4 times omega times G, over pi. Okay, so there's a lot here of just stuff we have to solve. Then we get to a point where we can actually apply the mass balance stuff we've been learning about. Okay, so at the end of the day, and I'm kind of guiding you here, that we want to solve a mass balance for n naught over n. So let's take a look at what the mass balance might look like. When we have a chamber, we actually have 2 identical chambers. Each of these are mixed, well mixed, with some volume. We know we have some reaction happening, and we are solving for K, putting all those things in. We have a flow rate. We have some initial number concentration going in, and some final number concentration going out. So this is then starting to look a lot like what we've been doing since the first couple lectures, right? So where we would say, if we reach steady state, and there's no indication that we wouldn't be at steady state, it's just, here's what it is, it's coming in, it's going out, and that's the way it continues, right? So we would say, given that problem, it would be reasonable to assume steady state. So we would write up a mass balance saying the accumulation term is 0, and that's going to be equal to what's going in, Q n naught, minus what's going out, Q times n, plus whatever reaction happens inside of there. And the only reaction we are aware of is a decay reaction, because we are having fewer and fewer particles as they stick together, right? So that's sort of the point, is we have a negative V in that volume. The K times n to the 1 power depends on how many particles are there. Another thing you could do to find the units for K and therefore know the reaction order here would be to look at your units of the K that we have the formula for, right? So we have this alpha, which is just a ratio. 100% of the particle collisions result in a new particle. So we know that's unitless. That's just a fraction. 4 is a number, pi is a number. Omega here we defined as a unitless volume per volume term. So that's also unitless. And so that leaves just g giving us a unit in per time. If you recall, this is going to be in seconds to the minus 1. So we know that k is going to be in seconds to the minus 1, or 1 over seconds. Okay, so all that told, we get this mass balance, and now we can solve that for, a lot of times we solve for n over n naught. In this case, we could solve for n naught over n, and that's where we can find the value here, given these other pieces we've come to. All right, and so once we have that, that tells us something about the volume of the initial particle compared to the final, the particle of the volume of an aggregate. Like I said earlier, the number of individual particles we started with in each of the final ones, that's going to tell us, well, if we had, a 5-liter particle and we've got 10 of those, now we have 50 liters of one particle, right? It's just going to be, the volumes are conserved, we'll assume they're both spheres, and we can solve with that comparison for a diameter. Okay, is that making sense, that path? All right, so I'm going to give you a little while to do that. I'll hand out these guys. And so work through that first. If you need a couple minutes at the end to kind of fill out the other questions, which is kind of how you're feeling about lectures in general, the topics, any other feedback you want to give me, I can give you more time at the end. But take 20 minutes to work on that problem, and give me your best shot, and we'll look at the answers in a few minutes. you guys feeling? Need much more time? A little bit? Take a couple more minutes to wrap up your attempt if you need it. I'll have you take a moment if you haven't as well to add any feedback on the back. I'll have you pass those forward in a couple minutes. All right, so let's pass those forward. All right. you feel better today having a little bit more of a walkthrough than last time? All right. Okay, so I'm gonna take a quick run through the solutions and a bit of an expansion on how we get there. I'll start by solving the mass balance here with you. When we work towards, and I'm going to erase a little bit of this here. We'll come back to it. When we solve for n over n naught, the way we can do that, we could say, well, first of all, divide everything by q is often a convenient thing to do. So we'll do that, simplify it a bit, and the v over q here becomes a theta kn. And we're really looking to get it into an n naught over n form. I'm going to add the n and the theta kn to one side, and then I'm also going to swap them back again and say, so this will be as if I added n to both sides, and then I added theta kn to both sides. And you'll see from here we can just divide everything by n and get to our desired n naught over n equals 1 plus theta kn, or excuse me, theta k. This should look a lot like the thing we did in class where we found that n over n naught was equal to 1 over 1 plus theta k. So you'll notice that that's just inverted, right? So that hopefully will feel good and familiar. And we can also double check that theta and k should both be in per seconds. If we've solved that correctly, then that should be unitless, and some concentration over concentration should be unitless, right? So that should all work out, assuming that we find theta and k in the same units. So let's work towards that. First of all, we could say theta, this is v over q. So we need to put q into cubic meters per second and put v into cubic meters. The volume itself was a 3.5 meters in every dimension cubic, so that's really simple. The volume is just going to be 3.5 meters cubed, or we could also write that as 3.5 meters and cube that. So that's like 42 something. I've got it in Excel. We can take a look in a moment. So theta turns out to be, if we do that, should be 326.3. Get this out of my way. Seconds. So that's part of this, and the only other thing we need here is k. Of course, we need a couple other things to get k. That would be our, we know that this parameter should be 1 because it's completely destabilized. The omega is something we needed to solve for. We need to make sure that we put everything in units that will cancel properly. So we'll start with n naught was 10 to the 5th number of particles per milliliter, and we need to take that to number per cubic meter in order to get everything in units. So that would be one source of an issue potentially. So that's really multiplying by 10 to the 6th. So this becomes 10 to the 11th particles per cubic meter. dP, we know by the problem this was 0.01 millimeters, so that becomes 1 times 10 to the minus 5th meters. Once we put those together, we can solve for a flock volume fraction, and that turns out that was 5.24 times 10 to the minus 5th. Now, if you stop and think about what this is saying, is like 5 millionths of a liter or of some given volume is is particles. So it's like 0.0005% or something like that. Of the actual volume, the whole volume is occupied by particles themselves. Okay, so that part is probably just unit conversions, making sure you have the units properly converted to meters. And then I skipped over G here, but G, we need to take the power in watts. We were given it in kilowatts, we'd have to convert that. The mu is given here, and again, we solved for the volume of the basin. So when we put in the term here, this should become 225.7 per second. So you can double check that you got the power in watts. Okay, so then that gives us everything we need to solve for K. So when we put those pieces into that equation, the K should come out to be 0.015 per second. Tracking so far? Is that good? Okay, so then, you know, in some sense, I went ahead of ourselves to do the n naught over n. You can do it later. You know, you could go stepwise. You know, you need all these pieces to find the K, and then, okay, how do I use the K? Or maybe it makes more sense to you to say, all right, let's go to the mass balance. I need a comparison here of the final and initial. Okay, and what do I need in order to solve that mass balance? Well, we need K, and step backwards from there. So either way it makes sense to you is you know, is totally fine. Well, it turns out once we have that K and we know the theta, it's really 1 plus theta K is our n naught over n. That part's pretty simple. So we put in those numbers and we should get a number of 5.90888. So 5.91 we'll say. That should be unitless, and we can move on from there. So that brings us to our final question here. What is the diameter of the aggregate? I already mentioned that the way we can approach this is we can take a look at the volume of the aggregate should now be really the number of the initial per final times that ratio times the volume of the initial particle. So the volume of one of the aggregates should be equal to the volume of 5.91 times the initial particle volume, right? That's just saying we've got about 6 of them, so the volume of one aggregate is equal to about 6 volumes of the original. From here, we can break that down into diameters to say the volume of the aggregate, that would be the dP, excuse me, the diameter of the aggregate cubed, ag cubed times pi over 6 would be equal to 5.91 times the dP cubed times pi over 6. The pi over 6 will cancel, and we can see that we can say the d aggregate cubed is 5.91 times that known particle cubed, and so we can just take the cubed root of each side and solve, and we end with a value of 1.81 times 10 to the minus 5th meters. And one thing we can check here is to make sure that this value is higher than what we started with, because we've reduced the number, we've compacted them together, and sure enough, what we started with was 1 times 10 to the minus 5th, and what we ended with was almost twice that size diameter. Okay, does that make sense? So it's pretty involved, but a lot of it's just, okay, we've got a formula, we've got to convert some units, put it in the right form, and do a little bit of geometry at the end, right? So it kind of goes in a lot of directions. like I said last time, these types of participation exercises, I typically give 80 to 85% of the credit just for being here and putting forth the effort. And so the correctness is just a small addition. And this is going to be balanced with, any other participation grades and my impressions. And I tend towards giving you, if I didn't take many participation things, I tend to give you free credit. Yeah.
So is the flow rate what's entering a single chamber or both chambers? Because I put my flow rate in half.
Okay, that's a great question, and I didn't clarify that here. Yes, you should put your flow rate in half. So Q should be half of the 3 mgd. So since the flow is split between these two chambers, then really what we want to do is look at just one of the chambers. We could consider the volume of the two chambers combined, but it gets a little weird because then our powers only end up put to 1. We don't want to do that. We just want to consider 1, and we know that if we have the same initial concentration going out and they're exactly the same type of chambers, whatever's coming out here is going to be the same coming out here. It's going to be the same coming out here, right? So you can just look at one chamber, and you just have to make sure you're dealing with this one chamber with the 1.5 mgd. So that's a very good question. Does that make sense? Okay. Got any other questions? Issues? Yeah.
I don't know. I think maybe I'm doing something wrong because I did that, but I got twice. I got 10.79 for I did not over it. I got that number as well.
Okay, so what, and there is certainly a chance I did something wrong, right? Okay, so let me, first of all, bring over my Excel sheet so you can take a look at that. Anybody else get the?
I got 5.91.
She got 5.91. Anybody else get 5.91?
But I used 3 instead of 1.5.
Okay, let's see if in my equations here, maybe I grabbed the wrong Q value when I solved for theta. Yeah, I did that wrong. So if you see here, what I did was I said, here's Q, and then Q for each of them. And when I went to grab the Q, I should have grabbed Q for each of them. That should give us 10.81. Yeah. So sorry for that confusion.
So
good job on that.
What would be the diameter? Did you use 591 for the diameter or 10?
Yeah, so I put in manually as 5.91. I should have actually just, so this should update if I put it like that. Okay, so the diameter should be 2.2 times 10 to the minus 5th instead of that other one. So I'll correct this in the page here. Move it back over here so that's easier for me to do. All right, thank you for catching that. It should be 2.21. And you can also see kind of how much wrong that would make it if you made that error like I did. So it'd be 10.82 really. So my theta here was wrong. That should be 652. And that means our K, oh, that didn't change. Okay. So omega's fine, and not over. All right. You have to go through the volume because the diameter is not necessarily conserved. If you think about what happens when you take, let's say, marbles, and you take two marbles and put them next to each other, the diameter lengthwise might double, but that's no longer a sphere. So if we assume that they somehow meld together and form a sphere, but conserving the same amount of volume that they had, you'll see that you have 10 marbles and it doesn't multiply the diameter by 10, right? They kind of meld together and fill the same. If they're filling the same volume, then it's it's the same reason if you want to get the most money for your most pizza for your money, you order a large diameter pizza, and so that means there's more pizza there because the area is increasing in that manner. Yeah.
So when I was doing it, what I did was we found n naught over n equals whatever. I then found n using that and changed n naught to n in the omega equation and then solved for diameter that way.
Did you get the same diameter?
I got, yeah, so I did I used 1 instead of 1.5 because I was just looking at conversion when I solved it, but I got 2.3, which is extremely close to 2.2.
So
I'm assuming it would have worked if I had to.
okay, I would encourage you to check that on your own time. So what you're saying you did is you solved for an actual value of n.
Yeah.
I see a lot of people try that, but I think you set yourself up for a distraction if you're not careful, because you'll get focused in on, okay, what is this n? But really the thing that matters is the ratio between the two. I think you might end up skipping the, what would you be skipping there? There's a chance that would work, but I see a lot of people try this type of problem by trying to find an n value directly, and miss the problem because they got stuck trying to do that. So see if you can make it work and get the same answer. There is a chance that what you're doing is essentially algebraically the same or the equivalent, but I know that has been a trap for a lot of students in the past, where they feel like they need the n itself, when in reality we actually just need the ratio there. Usually having a ratio like that just simplifies it and says, okay, we've got that ratio and we can go from there. But yeah, let me know if you find that, like, you work it out and algebraically it's just kind of the same thing there. Okay, any other questions or issues here? All right. So we're going to move on from there. I have one other thing I wanted to mention now that we kind of had this example that said two side-by-side reactors. Something I didn't really get to in our mass balance discussion is, well, sometimes we'll have multiple reactors in a series or side-by-side like that. So you've got a good impression of a side-by-side situation. The flow is split. If they're the same identical things, then you're basically you can treat one of them like we saw. Whatever's coming out of one should be the same thing that's coming out of the other because they're identical. Now, what happens if you have something in series? This can be quite handy. Sometimes, and in flocculation in particular, sometimes we will sequence them to have like a little bit of a faster flocculation and slow it down as we go to really encourage these larger and larger particles. So we might see scenarios where we have identical reactors, but they're in series. So we would say this is N0, N1, N2, and we could even go further, right, to however many N's we want. And what I want to mention here is that oftentimes we can have very nice simplifications, and it's worth stopping and taking a look at this so that you can adapt a solution across multiple mass balances to get one net mass balance. So let's consider each of these has some sort of volume 1, volume 2. The Q is really going to just be the same throughout. in this type of scenario. So then we have some theta 1 and theta 2. And you might be asking yourself, well, what if we had 2 or maybe even 3, and we wanted to know how much stuff is remaining after 3 of them? Or perhaps if we're doing flocculation, we could do n naught over how many particles initial versus the final. A lot of times we'll be looking for one or the other of those. So I'm going to write this as n over n naught. In this case, how about n2 over n0? Right? It's something we could certainly desire to know. How much did we remove if we used 2 of them instead of just 1? And what I want to point out here is that there's a nice simplification we can use if we recognize that we have some pretty good idea of what n1 over n naught is, and we have a pretty good idea for n2 over n1, given that we have the skills to do a mass balance on one of these, right? And we can do one at a time. So we could have some K1 and K2 here. Now, if we take a look at this, we could say n2 over n naught, we can find that just simply by multiplying one by the other, right? So that should give us, the n1s will cancel, that will give us n2 over n naught. So that is quite convenient, and what we can say then is, the overall mass balance for n1 over n naught, let's assume this is a first order decay. We could put in any type of mass balance here and then put in the appropriate algebraic formulation of it. But if this was a first order decay, steady state, then this n1 over n naught would look like this: 1 over 1 plus v1 over q times k1, right? Or theta k. 1 over 1 plus theta 1 k. Now, if they're all identical, then this becomes quite simple. Identical reactions, identical sizes. Then really what we have is 1 over 1 plus theta k times 1 over 1 plus theta k. And we could write that, again, for the condition that they're all identical, is 1 over 1 plus theta k squared. Okay, so that becomes, and we could put the brackets bigger, it doesn't really matter how we write that in this situation. But so long as we're squaring that. Regardless, this is a nice way to think about it. And what we're doing is we're saying, well, we know the ratio coming out of the first one, and we can multiply that by the ratio coming out of the second one. That will cancel nicely for us, and we can find the ratio from the start to the end. So keep that in mind. It's not always going to simplify to this, but it certainly can if we have identical systems. If you really cared to look at the math, this is actually the way you can get to the plug flow reactor mass balance as an infinite number of small CSTRs, one flowing into the next. Because if you have that type of a system and you have an infinite number of them, this 1 over 1 plus theta k, raise that to the infinity power, you end up with the same n over n naught equals e to the minus kt. So it actually gets you there mathematically. We just talked about it as a batch reactor flowing through a system. Turns out if you do an infinite number of those, you get that, that's probably some expansion series of some sort. And the math ends up working out. So that's kind of the plug flow example. Okay. A little bit of an elaboration here if you're curious about that from some other notes. Okay, so I'm going to stop that one here, and we're going to get on to our granular filtration. So we just have 20 minutes. I think we can get through most of this here. I'm not going to work this one out at the moment, but if you were interested in some practice on the sequential reactors sort of things, here's a problem. I'm just going to kind of read it, and we can reflect on it for a moment. It says if you have two 8 cubic meter reactors, each with bacterial growth, reactions occurring within them, so some sort of rate constant, flow rate through them, incoming concentration. The question is, what is the final concentration of bacteria in the first reactor? If the first is a CSTR and the second is a plug flow reactor. So what we're looking at is some case where we have bacterial growth in here, and then we go through a plug flow reactor and coming out there. So you can use the same series type of analysis, but of course you have to treat these accordingly to the appropriate mass balance there, where we'd have N0, N1, and N2. So if you're interested, you can give that a shot, and if you'd like, we can talk more about it next time. But for the moment, I want to move on to filtration. Okay, so there's 2 types of filtration. We'll cover both. There'd be membrane and granular. We're going to start first with granular filtration. This is filtration that's not technically size exclusion. And the way we would normally do this is have some water over some bed of sand or grains of some sort. This would be a lot like dripping coffee through a bunch of coffee grounds. The grounds would technically catch some particles in solution. Of course, we're actually using it in reverse and kind of extracting stuff from the coffee. But that type of dynamic, flowing water through a granular media like that, could catch particles. Whereas the coffee filter itself, the filter paper, is acting to exclude the coffee grounds by size. So that you've got both scenarios in the coffee scenario. You've got size exclusion, which is what we say for membranes. We have some particles, they're trying to travel through, and they get stuck on the surface because they're too big, right? Draw those a little bigger. Small ones would make them through, be like mosquitoes in a screen porch, right? Hopefully, mosquitoes are not so small they can fit through the mesh. Hopefully you don't have any holes allowing things to get through. The granular system, we would probably be flowing this through like that. Particles are going to get stuck more likely because they just happen to stick to a grain or find another particle along their way and get stuck like that. So we have what we'd call adsorption reactions or adsorption occurrences, where it's sort of like Velcro, where a particle sticks and it just kind of gets stuck, right? We talked about particles sticking to one another. Well, the same destabilization principles would allow them to stick to a sand grain. So it's not that there's not enough space in the pores for them to travel through, because there usually is. It's more so that they are getting stuck along the way. So I mentioned coffee. Maybe a better example would be a Brita filter, where we're passing the water through. It can actually remove some chemicals, even though the chemicals are molecules and really, really tiny, but they happen to stick well to that black carbon stuff, and so they get stuck and stay and are removed that way. So there's a few different ways to look at this. Like I said, we're not usually counting on mechanical screening. That is if our particle is just simply too large to make it through the pores. That's more of what we're talking about when we're doing membranes. Can happen, but that's not the focus of granular filtration. We'll say not the intent or design, I guess. because then you just fill up the top of the thing with a layer of mud, and nothing else would go through very easily. We do that type of process with membranes on purpose. Okay, there might be sedimentation. The particles would just literally have a tiny little sedimentation chamber in the pores, and it would be called sedimentation. Maybe this is allowing particles to do more flocculation and grow larger, and then in the middle of the sand, then they're mechanically screened out because they've just gotten too large, because they've had this nice time to interact with one another in sort of a gentle flowing environment. Maybe they're intercepting the side, so you see right here this particle's moving through, and it just happens to hit the edge, and it gets stuck, and so it stays, right? So a lot of ways where maybe they're just getting stuck. Maybe the water is flowing in one direction, makes a sharp turn, and the particle keeps going straight a little bit, impacts the surface. All of these like physical processes are just pieces of the puzzle of why it kind of works. And essentially what we get at the end is particles that are stuck, but not like permanently stuck. So if we're not careful, they could eventually make their way out. And on the flip side, we can backwash this and flush them back out once we've caught them all in one batch. So in practice, there's a few ways this would look. You could pack a column. We've got some in my lab if you're curious to see this. And hopefully in the next week or two, this is actually this little palette, three columns of granular media here. It's actually going to be borrowed by a consulting company, and we've got a student who will be helping that and doing that as a bit of a project. So if you're interested, we might have an opportunity to see that in practice. It's granular filtration. And in this particular case, it's a little bit more advanced because they're trying to use it for iron and manganese removal. So not just particles, but that adsorption process will allow for for iron and manganese to precipitate out on the surface, and they have some special media to do that. So sometimes it gets a little more specialized into that adsorption and removal stuff. But this is a neat thing. Right now we just have it hooked up to the tap water as a way to pressurize it, so we could run it, backwash it, and kind of see that in action. You might have larger scale ones where you've got these big tanks. The more common in water treatment would be to fill up a bed kind of like this you see here. It might be several meters wide and 10, 15 meters long, and they're just packing it with essentially sand. Sometimes you'll have partly sand, partly activated carbon granules, and you have like a two-layer, two-media system. One media may catch a particular type of particle better, and the other can catch the other stuff that's not so much by the first. So get some variability there. Here's another example, just lots and lots of these chambers. And so these are kind of a basic filtration setup. And if you think about groundwater, this is kind of what happens with groundwater, right? Water flows through sediment, through the dirt, through the soil, through the pores, and any particles in there tend to get stuck. So when you extract groundwater, it's generally free of particles that you might find in a river, right? It kind of has that natural filtration type of dynamics. The first time these were used was actually 1800s as slow sand filters. Those were more biological treatment in essence, giving them a lot of time to just slowly seep through, and that means biofilms would grow and be degrading some waste. So that was some treatment, usually for more like a wastewater setting, but could theoretically be used. We use, in that context, now what we use today would be called rapid sand filtration or granular filtration. Okay, so there's a few terms we want to deal with to describe them and to design a system. The design itself is pretty straightforward. The real deal is we have to account for the time and water used for backwashing. So it's kind of like we're just going to say we get X amount of water from our system, but we have to backwash every so often, and that takes an entire filter bed offline. And so we have to do two things. We have to have enough filter beds to continue producing water as normal, to meet the demands of our community, municipality, while also taking some of that water and sending it backwards through and accounting for that water loss because that's no longer usable. So it's like what we're going to deal with is pretty simple math that tells us, okay, how many filter beds do we need given our backwash requirements? So we're just going to be doing some volume accounting. And to do that, we just have a few terms here about the filter operation. We would say the ripening would be kind of a warm-up phase where the first few minutes of operating is like opening up a brand new Brita filter and you start operating, you see the black specks coming out. If you've ever done that, what you'll notice is some stuff is escaping, some particles, until things get compacted and settled nicely. So if you backwash a filter or you have brand new media, there's going to be some junk coming out the first few minutes. Things will settle into place and you'll get cleaner water after 20 minutes of operation, something like that. So that's the ripening stage. Every cycle after we backwash, there's going to be excess particles coming out at first, and we don't want to drink that, so we actually send that to waste as well. So this is essentially becomes wastewater. Then we have the backwashing itself, obviously wastewater. Sometimes we also inject air to shake it up. We'll watch a couple little videos to kind of see this in action. So the backwashing, there's two things to consider here. One is the amount of time that we're not operating and producing water, and two is the amount of water we're using. So both of those goes into our total net volume accounting. At the end of the day, it was going to feel stupidly simple, but we'll take a look at the math and stuff to say, okay, here's our actual filter efficiency on a water basis, and here's our effective flow rate or loading rate, as we'll see, in terms of effectively this filter is producing this amount, and so this is how many filters we need. So that's our target. Another parameter here would be head loss. This is talking about hydraulic head in terms of the amount of pressure required to push our water through these filters, not membranes. And essentially, we often use gravity and just load water on top of these filter beds and let the gravity push them through at a given flow rate. And if we're feeding a set flow rate, then the water, there becomes more resistance from all those particles in there, the water is actually just going to stack up a little higher to increase the pressure through to match the amount of flow rate that we're trying to get out of it. So it's actually a pretty self-managing processes, which is quite convenient. But at some level, we risk too much pressure, and then water fissures through forces a crack, forces a fissure through the water, through the sand, and our treatment goes out the window. So we have to watch for the head loss at some level. We've reached some height. We say, okay, we've got to stop and backwash now. Turbidity, the final one, we've talked about this. You probably know a lot about this. The light scattering of particles. This is a critical parameter to monitor to know whether or not our treatment is still happening properly. So most systems will have online turbidity monitoring. And if you recall, I assigned you guys that cryptosporidium outbreak paper. Now would be a good time to revisit that. I'll be assigning a quiz at some point on Moodle for a part of participation. One of their issues was they had these granular filters and their turbidity monitors that were supposed to be running were not operational. And so they missed the fact that they were discharging a whole lot of particulate matter straight into our drinking water, well, into Milwaukee's drinking water, causing a very big outbreak. Okay, so just a couple quick slides here and then we'll wrap up. This is just a kind of an example of no turbidity to high turbidity. Again, it's kind of that cloudy sort of effect. There are a few ways to measure it if you're kind of looking maybe out in a lake or river. This Secchi disc is one way to do it at the point where you can no longer distinguish the colors. You can kind of see that in action here. You would measure the distance at which that becomes impossible due to light scattering. You can kind of see that a little bit right here. Okay, so we'll pick up here next time to really see, okay, how are we going to determine the frequency of backwashing that's necessary in order to manage a filter properly. Okay, thank you for your participation today, and I'll see you guys on Tuesday.